In this video, we will look at why does P series converges when P is greater than 1. In the previous one, we have seen that P series actually diverges when P is between 0 and 1. It might be equal to 1 also, so that makes it a harmonic series. Now, what happens when P, when P is greater than 1? So, you have a series Sn, where Sn is the sum of n terms like 1 upon 1 to the power P plus 1 upon 2 to the power P plus so on and so forth till 1 upon n to the power P. Now, does it converge or does it diverge as P is greater than 1? Now, when P is between 0 and 1, is in this interval 0 and 1, it diverges. Now, An, which is the sequence from which this series has been made. Now, An, which equals to 1 upon n to the power P, it's a positive series, it's a sequence of positive terms, it's a sequence of positive terms. What we need to find out, when you have a sequence of positive terms, you need to find out whether the series Sn, it's bounded or not. Because the moment you know that it's bounded, it will be convergent because it is a monotonic, it is made up of a monotonic sequence, which is only a sequence of positive terms. So that's by the theorem that we have done previously, we know that. Now, Sn is essentially 1 upon 1 to the power P plus 1 upon 2 to the power P plus 1 upon 3 to the power P and so on and so forth. Now, this is bounded when P is greater than 1. Now, why is it bounded when it is when P is greater than 1? For the simple reason, we look at when P equals to 2. When P equals to 2, the sum is essentially finite. Why is it finite? Because just look at the denominator. The denominator is increasing because it's in power which is greater than 1. That means that the term would be decreasing. So the terms are decreasing. The terms are decreasing when the denominator is increasing. And to give you a proof of this, we look into the following. Let's look at the function fx, which looks like 1 upon x squared. So it's same as our sequence an. So let's treat an as our function 1 upon x squared. So summation of 1 upon x squared, which is our Sn, that is same as the area under the curve 1 to infinity 1 by x squared. Now, what is this area? So we will look into what this area actually is. Now, this area actually will be, the integral. If you open it up, the integral will be 1 upon 2 squared into 1, 1 upon 3 squared into 1, 1 upon 4 squared into 1, and so on and so forth. That will be the area under the curve, right? So, when I apply it to my summation n square, 1 upon n square, essentially I have one extra term 1 here and this area. So this integral 1 to infinity 1 upon x square. Now 1 to infinity 1 upon x square, this area essentially equals to 1. And why does that happen? The reason is that, just look at it. You have integral 1 upon x square. Let's use integration out here from 1 to infinity. Now, it is same as saying, limit t tends to infinity 1 to t 1 upon x square dx. Now, just integrate 1 upon x square, we get minus 1 upon x from 1 to t. So, essentially, you have 1 minus t and just put the limits. The moment you put the limits, you get this should be 1. So, this area essentially is simply 1. So, that means 1 upon summation 1 upon n square is less than or equal to 2. It's less than or equal to 2. So that means that it is bounded. And similarly, so this partial sum is bounded. Similarly, other partial sums are also bounded when P is greater than 1. Other partial terms are also bounded. And because it is bounded, It is convergent. The moment you know that it is bounded, it is convergent. So P series will be convergent when P is actually greater than 1.